Welcome, everyone. I'm excited to kick off today's presentation with a fascinating topic, the wave nature of particles, electron diffraction. Unveiling the quantum world. Today, we'll explore how electrons, which we often think of as particles, actually exhibit wave-like behavior under certain conditions. We'll look at some key experiments, the principles behind them, and what they reveal about the nature of matter at the quantum level. So, let's dive in and discover the intriguing wave-particle duality that shapes our understanding of the microscopic universe. So, here we have a fascinating moment in scientific history from October 1927, which is often called a radical idea. It's also known as a puzzle from Paris, because it challenged how we traditionally understand particles and waves. Back in 1924, the French physicist Louis de Broglie proposed a truly revolutionary idea. He asked, what if all moving particles also behave like waves? This was a huge leap forward because, up until then, classical physics saw particles and waves as completely different. Particles were tiny, solid bullets. Think of small, solid objects, while waves were seen as ripples on a pond, spread out and wave-like. They were considered opposites, with distinct properties, but de Broglie suggested that maybe this distinction isn't so clear-cut. Could an electron, which is a fundamental particle of matter, really have a wavelength? That was the big question. If true, it would mean that particles, which we usually think of as discrete objects, could also exhibit wave-like behavior, something that would turn our understanding of physics upside down. This idea laid the groundwork for the wave-particle duality, a key concept in quantum mechanics, and really pushed the boundaries of what we thought was possible at the time. Let's take a closer look at what's often called the crucial experiment that provided key evidence for wave behavior in particles. This is the Davison-Germer experiment from 1927. So, here's how it was set up. A beam of electrons was fired at a thin nickel crystal. Now, according to classical physics, if electrons were just simple particles, what would we expect to see? Well, they should either pass right through the crystal or scatter randomly in all directions. This would create a bright spot in the center with a diffuse glow around it, nothing too surprising. But here, where it gets interesting, what they actually observed was completely unexpected. The pattern was not what classical physics predicted at all. Instead, it showed a diffraction pattern, similar to what you see with waves, like light or sound. This was a huge breakthrough because it provided direct evidence that electrons, which we normally think of as particles, can also behave like waves under certain conditions. This experiment really challenged the classical view and helped pave the way for the development of quantum mechanics. It showed us that the behavior of particles at the atomic level isn't just about particles. They have wave-like properties too. And that's a key piece of the overall story we're exploring about the wave-particle duality. So the result we saw was truly shocking. Instead of a random distribution, the electrons created a wave pattern, which we call a diffraction pattern. Now, this pattern isn't just any pattern. It's made up of distinct, concentric bright and dark rings. And what does that tell us? Well, this is a hallmark of diffraction and interference, phenomena that are exclusive to waves. What's really fascinating is that this pattern looked exactly like the one produced when X-rays, which are well-known waves, pass through a crystal. This similarity was a huge clue. It provided the first direct evidence that particles, like electrons, can behave as waves. This discovery challenged our classical ideas about particles and waves, and it was a major step toward understanding the wave-particle duality at the heart of quantum mechanics. Let's talk about wave interference, a fascinating phenomenon that occurs when two or more waves meet. Essentially, wave interference is about how waves interact with each other, whether they amplify or cancel out. When waves meet in phase, meaning their peaks and troughs align, they combine to create a larger, more powerful wave called constructive interference. This is what causes certain areas to have higher energy. On the other hand, when waves are out of phase, think of a peak meeting a trough. They cancel each other out, leading to destructive interference. This can create areas of reduced or no wave activity. Understanding wave interference is crucial because it explains many phenomena, from the patterns of light and sound to the behavior of antennas and even the ripples on a pond. It ties directly into our overall theme of wave behavior and helps us grasp how waves can influence and interact within different systems. So what does this pattern actually mean? Let's start with the bright rings, or the maxima. These are the places where constructive interference occurs. That's when the electron waves arrive in phase, meaning the crests line up with crests and the troughs with troughs. When this happens, the waves reinforce each other, creating those bright, prominent rings. On the other hand, we have the dark rings, or minima. These are points of destructive interference. Here, the electron waves arrive out of phase. The crest of one wave meets the trough of another. When this occurs, the waves cancel each other out, resulting in those dark, less intense rings. What's really important to understand is that this entire interference pattern provides clear and undeniable evidence that electrons behave like waves. It's a key piece of the puzzle in understanding their wave-like nature and how they interact in these complex experiments. Today, I want to talk about electron diffraction through a graphite film, which is a fascinating way to explore the structure of materials at the atomic level. When electrons pass through a thin graphite film, they don't just go straight through. Instead, they diffract, creating a pattern that reveals a lot about the material's internal arrangement. This diffraction pattern is like a fingerprint for the crystal structure of graphite. It helps us understand how atoms are spaced and arranged in the layers. This technique is incredibly important because it allows us to analyze materials without destroying them, providing insights that are crucial for advancements in nanotechnology and materials science. Connecting this to our overall theme, electron diffraction through graphite exemplifies how atomic-scale observations can lead to a deeper understanding of material properties, which is fundamental for developing new, innovative technologies. Let's take a closer look at the deBroglie wavelength. This equation is really fascinating because it connects the worlds of particles and waves. deBroglie proposed that every particle has a wavelength, and this wavelength is related to its momentum, which is the product of mass and velocity. The key equation here is lambda equals h divided by p, where lambda is the wavelength. Now h represents Planck's constant, which is a very tiny number, about 6.63 times 10 to the minus 34 joule seconds. And p is the momentum, calculated as mass times velocity. What's really important to understand here is that the wavelength is inversely proportional to the momentum. So, as a particle moves faster or becomes more massive, its wavelength gets shorter. Conversely, slower or lighter particles have longer wavelengths. This relationship is crucial because it helps us see how particles can exhibit wave-like behavior, especially at very small scales. It ties perfectly into the overall theme of quantum mechanics, where the distinction between particles and waves becomes blurred. So, in essence, this equation tells us that the faster or more massive a particle is, the less wave-like it appears. And that's a key insight into the nature of matter at the quantum level. All right, let's look at this example. We have an electron that starts from rest and is accelerated through a potential difference of 20 kilovolts. Our goal here is to find its deBroglie wavelength. First, it's important to understand that when the electron is accelerated by this potential difference, it gains kinetic energy. The amount of energy it gains is equal to the charge of the electron multiplied by the potential difference, which is E times V. Since the electron starts from rest, its kinetic energy after acceleration is Ke equals E times V now, plugging in the values. E is 1.6 times 10 to the minus 19 coulombs, and V is 20,000 volts or 20 kilovolts. Next, to find the velocity of the electron, we use the kinetic energy formula Ke equals 1/2 times m times v squared. Rearranging, v equals the square root of 2 times Ke divided by m. By substituting in our values, Ke from earlier and the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms, we can solve for v. Once we have the velocity, the final step is to find the deBroglie wavelength, which is given by lambda equals h divided by p, where p is the momentum, m times v. Using Planck's constant, h, which is 6.626 times 10 to the minus 34 joule-seconds, we divide that by the momentum to find the wavelength. This example nicely illustrates how particles like electrons exhibit wave-like properties, and how their wavelength depends on their energy and velocity, central ideas in quantum mechanics. So, by calculating the deBroglie wavelength, we see the wave nature of electrons becomes evident, especially at small scales. Now, let's take a closer look at the solution. Here, we're focusing on the key points that can truly make a difference. First, it's important to understand that implementing these strategies requires a tailored approach, considering the unique aspects of each situation. The most critical concept to keep in mind is that sustainable change often depends on a combination of technology, process improvements, and people engagement. Connecting this to our overall theme, these solutions are not just quick fixes, they're part of a long-term vision for growth and resilience. By adopting these strategies, we can effectively address the challenges we've discussed and set the stage for future success. Let's look at this example involving a proton and an alpha particle, both accelerated through the same potential difference. The key question here is, which of these particles will have the longer deBroglie wavelength? Remember, the deBroglie wavelength depends on the particle's momentum. Since both particles are accelerated through the same potential difference, they gain kinetic energy proportional to their charge. The proton, having a single positive charge, gains a certain amount of energy, while the alpha particle with two protons gains twice that amount. This means the alpha particle ends up with a higher kinetic energy, and therefore a higher momentum. Because the deBroglie wavelength is inversely proportional to momentum, the particle with the smaller momentum will have the longer wavelength. So in this case, the proton, with its lower momentum, will have the longer deBroglie wavelength. This example really highlights how the particle's charge and resulting energy influence its wave properties, connecting to the broader theme of wave-particle duality and quantum behavior. Now, let's take a closer look at the reasoning behind our approach. First, it's essential to understand that our decisions are grounded in thorough analysis and data. We aim to ensure that every step we take aligns with our overall goals and contributes to the bigger picture. By carefully considering each factor, we can identify the most effective strategies and avoid potential pitfalls. This reasoning process helps us stay focused and makes our actions more deliberate and impactful. Ultimately, connecting these points to the overall theme emphasizes that thoughtful reasoning is the backbone of successful decision-making. It's what transforms information into meaningful actions that drive our progress forward. In summary, what we've covered today highlights the key points that tie everything together. We've explored the main concepts, the challenges, and the opportunities that come with our topic. It's important to remember how these ideas connect to the overall theme of our presentation, emphasizing the significance of understanding and applying these insights. By keeping these points in mind, we can move forward more confidently, informed by a clear overview of the essential takeaways. Thank you for your attention and engagement throughout. Thank you so much for your time and attention today. I truly appreciate your engagement throughout this presentation. I hope you found the information helpful and inspiring. Remember, the key takeaways are about applying what we've discussed to make a positive impact. And with that, I want to wish you all a great day ahead. Take the insights you've gained here and go out there confidently. Thank you once again, and I look forward to seeing the great things you will accomplish.